Our first presenter is Dan Lee, so let's give her a warm clap.
Thank you, Luma. Thank you, everyone. Today, my talk is about tractability assumption and model holism in models. My co-author Ryan O'Loughlin is here today as well, so he might jump in for Q&A session if there's any questions that I can handle. Here's the outline for my talk. First, we start with what is a model, what is a robust model, what robustness analysis does. Then I will introduce a central question that we're trying to answer. Does robustness analysis go wrong in certain convolutions? Our solution uses a conceptual framework of model robustness by Lloyd and highlight two types of independent evidential support. One is error analysis, the other is empirical evidence. First of all, what is a model? Apparently, model is a heavily loaded term. People build models based on various theories and observations and use these models for a variety of purposes. My favorite account describes a model as a story with a specified structure. First is a story, a narrative about what's happening. Second, it comes with a specified structure. In modern science, this structure usually refers to a logical or a mathematical structure. In an economic model, for example, the story is often about all sorts of agents and their interactions. The structure is the various functions that describe these agents and interactions. Besides being descriptive, a model also ought to be explanatory about the target phenomenon or system. Ideally, we can use models to make projections. I know in reality, some models don't have all these traits at the same time. Some are more descriptive and explanatory, while others are more predictive than explanatory. For example, statistical models. This is only an ideal picture of what a model should be. The example that I'll be using today mainly come from climate science and economics. A good model should also be robust. What do I mean by robust? A robust model should first represent the causal mechanism properly. Second, it's insensitive to confounders. Models are selective representations about the real-world system in the sense that they only represent some aspects. It is inevitable that modelers have to make decisions about what to include and what to leave out, and make assumptions about what they do not know yet. For example, in a zero-order global climate model, the Earth is treated as a dot. We only consider radiations. In this case, the causal mechanism that we're interested in is really the heat equilibrium caused by the solar radiation. Possible confounders could include our assumptions about the radiant emittances and other parameters. A zero-order climate model possibly can be executed within a few lines of Python code. But real climate models are really complex with many modules and considerations built in. Usually it's very difficult to analyze, and this is where we need robustness analysis. Imagine we're building a global climate model and we sort of know greenhouse gas, GHG here. It's causally relevant to the increasing global mean temperature. But there are still some details to be spelled out to build a model. For example, how do we characterize the greenhouse gas? How do we characterize the globe? We need a set of parameters. But since the computation is complex, as a concept causing the increasing temperature projections, or is it a particular set of parameters that represents greenhouse gas? A robustness analysis will require you to swap out this set of parameters with a reasonable new one. And then if the new result or projection stays reasonably close to the original one, you know that this result is robust across two different sets of parameters. Also, parameter is one of the many assumptions that you can swap in a robustness analysis. Again, models are complex, they're not Lego blocks. Different components, so when you swap some assumptions, boom, it blows up. Okay, I've been waiting for this moment. Now, seriously, what do I mean by blowing up? When you swap one thing with another, it's possible that the whole structure of the model changes. Maybe some magic structure of the model changes. Maybe some magic reaction happens. The model is not the original model anymore. This is a model version of the shape Theseus, the model of Theseus, if you may. The problem of holism could potentially invalidate the robustness analysis as a methodology. So this is a serious philosophical quote tried to address the following issues. Do trackability assumptions introduce holism? Can we use robustness analysis? And are there any solutions? First, what is a tractability assumption? Tractability assumption is a heavily loaded term, apparently. But since we're working with a heavily loaded term, apparently. But since we're working with the case studies, and I will use a definition from an article that I'm arguing against. When Lysandra was raising the issue of holism with tractability assumptions, her definition is tractability assumptions are assumptions that omit aspects of target system in order to facilitate mathematical tractability. Circular. Let's make the circle a little bit bigger by examining some examples that she uses. For example, representing continuous time as discrete, which is a common trick in computer simulation, or treating population size as continuous when it is discrete in reality. Other examples include assuming some relationship to be of a particular form or property, like assuming goods will melt away during shipping. We'll go details into this shipping example later. So all these tractability assumptions have one thing in common, is that they serve for the pragmatical purpose, that is to make the computation simple enough. They play a special mathematical role in the model. In contrast, there is very little theoretical justifications for the adoption of these assumptions. Now return to the central issue. Can we still use robustness analysis for tractability assumptions? Lysandra provides an argument against robustness analysis in the case of tractability assumptions. She says, however, it's often the case that intimate connections between simplifying assumptions and mathematical tractability is such that variation can often only be introduced by altering the overall structure of the model. As the result has to be taken as a whole, has to be taken as determined by the model as a whole, not a case of robustness analysis where a single or few assumptions have been replaced with a different one to assess their impact on the result. What does she mean by overall structure of the model, or how do we treat model as a whole? About model holism can lead one to think that tractability assumptions are a huge problem for robustness analysis. Before looking more closely at her argument of model as a whole, we need to know a little bit more about the case study that she presents, the core periphery model, or CP model. It is a geographical economic model, the central model. It is a geographical economic model. The central question that they're trying to answer is how economic activities agglomerates in the core areas and how they disperse in the periphery areas. A real life example would be the population size of Beijing has doubled to 21 million in the last 3 days. This is an effect of the agglomeration that economists are talking about. The result of the CP model is that, while other things being equal, spatial agglomeration occurs when economic scales are high, market power is strong, and transportation costs are low. Here, the transportation cost represents a crucial aspect of the causal mechanism. It is quite intuitive because you would assume the goods shipping between the core and the periphery areas would be a causally relevant factor. One assumption about this transportation cost is called iceberg assumption. That is, goods melting, their value is assumed to be diminishing as they are shipped further away. And the main reason it was adopted in the first place is its mathematical form works well with other parts of the model, making the model tractable. Hence, it was initially a tractability assumption, not an empirically or theoretically derived function. I'll return to Lysandra's argument. She argues that it is difficult to replace the iceberg assumption or the iceberg function with other functions because it is not guaranteed that if a certain feature such as price increases convexly with distance needs to be tested, then the model can be built where the feature price is concave with distance is reintroduced, while all the rest remains as before. The convexity of the transportation costs follow from the mathematics of the models as a whole. Consequently, if you can't swap it out, then robustness analysis is of no use. We disagree. We think her argument is insufficient. Our rebuttal consists of 2 steps. Step 1, making a distinction between modeling component, its mathematical formulation, and the property of that formulation. In this case, the modeling component is the transportation costs. The mathematical formulation is a iceberg form. The mathematical property is whether that function is concave, convex, or monotonic, and so on. She misinterprets what robustness analysis does. Let's recall what the robustness analysis does. We swap out the confounding factors, and hopefully the result still holds. This means on the confounding factors. In the CP model, we want to keep the modeling component, the transportation cost, because it's central to the causal mechanism that we want to study. But exactly because we don't know what the real transportation costs look like, we also want to make sure that the result we get does not depend on a particular formulation of this transportation cost. So we swap the function with the new one and see if the result still holds. Each mathematical formulation comes with its own mathematical properties, but it doesn't matter to robust analysis, because what we are concerned here is our result does not depend on some of that transportation cost. This is why Lysandra's argument is insufficient, because she's assuming that the mathematical property of these formulations have to remain the same. Robustness analysis does not require mathematical property to remain the same. On the contrary, it aims to vary these mathematical formulations. And by the way, someone did swap it out with a linear function, and the result still holds. Although her argument is insufficient, the problem of holism with tractability assumptions still remains. That is, given the pragmatic role of tractability assumptions in a model, that is to make a model tractable, we want to know if this analysis can still be applied and give us meaningful result. So these are some general accounts. There are potential candidates as frameworks to address the holism issue. However, they have one thing in common, that is there is no place for auxiliary assumptions, that is such as tractability assumptions. It's not very surprising because all they focus is on the logical relationship between evidence and hypothesis, or the security of evidence, as you can see here. Since the auxiliary assumption is something that can swap out, its role in these accounts is probably trivial and negligible. However, if we never talk about this, tractable assumptions in these accounts, then the holism problem that Lysandra proposed is not solvable based on these accounts. So they're not applicable. Okay. We propose to use the notion of model robustness from Lloyd 2015. There are 4 ingredients. I'm going just to emphasize 4 ingredients. I'm going just to emphasize 2, B and D. B is about the independent experimental evidence for the causal core. D is about evidence for the auxiliary assumptions. This is what we need to address a holism issue involving tractability assumptions. Item D, some evidence for each assumption. Potential support I'm talking about here. We think there are at least 2 types of evidence that modelers should consider in the case of tractability assumptions. First is from applied mathematics, such as error analysis, and I will be explaining in a second. Second is empirical evidence, and I'll be explaining using the iceberg assumption case that we just touched on. I don't have time to go into details about this, but a sum up for this slide is applied mathematicians modify the original problem to be tractable, and use a solution of this engineered problem as an approximate solution to the original problem. In order to make sure that the approximation is not too far off, they use this approximate solution to estimate the shift in the input space, that is x here, the delta x here. If the delta x is smaller than the modeling error, then this approximate solution is considered to be satisfying, caused by the tractability assumptions can be estimated. And I'd also said a second type of evidence is empirical. Iceberg assumption in the CP model states that goods melt away at shipping. You know what? Surprise, ice melts. So Bosker and Martin used the ice shipping historical records from 18th century and analyzed how ice would melt in shipping. Of course, various factors are involved, such as the insulation on the ship, whether the route in the tropical areas, etc. One of the conclusions is that if the remaining variations were noise, iceberg transportation costs in practice quite well. They're basically saying iceberg assumption is reasonable only to a certain degree. I think the main point here is that since most of the concepts in economic models have an empirical meaning, why not use them? Okay. Here's my takeaway message. Holism doesn't imply holy crap. So don't panic. Holism doesn't imply holy crap. So don't panic. Tractability assumptions can be evaluated in two ways: error analysis and empirical, possibly more ways. Robustness analysis, model robustness as a philosophical concept is more explicit and useful as analytical tool to address this holistic general and traditional accounts. Thank you. Thank you for your patience.